Hi, today we are going to discuss the divergence theorem. So, what does it consist of? Conceptually, this theorem can be seen as an extension of the Green's theorem. They are similar since both of them allow to determine the flux across the boundary of a certain region, and for that, using a derivative function, which in this case is the divergence of f. When we use the Green's theorem, we are working in the two-dimensional region, so the boundary is a curve. However, when we use the divergence theorem, we work with a three-dimensional region, so the boundary is a surface. Let f be defined by pi plus kj plus rq. To apply the equation above, we need to evaluate the divergence of f, and that can be assessed by adding the partial derivatives of f. This means that we can rewrite the definition of the theorem as such. Let's see an exercise. Here, you are asked to evaluate the flux across a surface S using the divergence theorem. You know that f is defined as x power 2 yzi plus xy power 2 zj plus xyz power 2k. You are also told that S is the surface of the box bounded by the equations that are appearing in your screen, where A, B, and C are positive numbers. For a better understanding, let's start with a sketch of our surface. And let E be the box solid region and S its boundary. First, we need to determine the divergence of f, and for that, we resort to the definition. So, we proceed to add the partial derivative in respect to x of x power 2 yz plus the partial derivative in respect to y of xy power 2 z plus the partial derivative in respect to z of xy z power 2. We get 2xyz plus 2xyz plus 2xyz, which is 6xyz. Resorting to the divergence theorem equation presented in a theoretical explanation, we can say that the flux across S is equal to 6 times the triple integral over E of xyz dv. Now, we just need to define the region E, where x is found between 0 and A, y between 0 and B, and z between 0 and C. With that being said, we can rewrite the previous expression as 6 times the triple integral from 0 until A for x, 0 until B for y, and 0 until C for z of xyz, dz, dy, dx. As we already know, integrate first in respect to z, only then in respect to y, and finally in respect to x. After that, it's just a question of solving the triple integral. And then, at the end, you should get 3c power 2 b power 2 a power 2 divided by 4.